is like x plus y equals negative 14. And then it's 3x minus 5y equals 14. And then it just, all it says is solve each system by substitution or elimination.
Okay. Well, usually when it's in standard format, like this, both of these are, it's easier to solve it by elimination, at least in my opinion. If one of the equations is, for instance, if the first equation would have been this, same equation, but different format, then I would solve it by substitution, because I've already got y completely defined. So wherever I saw y in the second equation, I would substitute x minus 14. Okay? So, but it's not defined that way. That would require an extra step. So what's the best way for me to solve this by elimination?
So like cancel out one of the terms?
Well, if I add or subtract these two equations right now, I don't eliminate anything.
Oh, so multiply it so that they're like...
There you go. You got to adjust one of the equations so that you can add or subtract it and get rid of a variable. So what would I do?
Could you times... I don't know, so it's like positive 5y.
Okay. So you're saying multiply both sides of equation number 1 by 5, which gives me 5x plus 5y equals minus 70. So this used to be equation 1, now this is equation 1. And I actually do find it helpful to number these. Not so necessary if you're just doing two variables, but the moment you get a third variable, it's really helpful to number them.
Okay.
Now what? In other words, that's no longer my equation 1. I got equation 1 and 2, and now I got it set up so that I can do what to get rid of a variable?
So then you can cross out the 5y.
Well, you can't just cross them out. You have to add the two equations. This is an important concept. If you have a plus b equals c, and you have x plus y equals z, I can add any two equations. So a plus b plus x plus y equals c plus z. I can also subtract any two equations. So those are the things I'm allowed to do, is add or subtract equations. Well, if I add these two equations, what do I get?
8x equals negative 56.
Which means x equals minus 7. Now, how do I solve for y?
Plug in an x for one of the equations.
Which one?
It doesn't matter.
Well, it matters, and you want to choose the easiest one. In other words, math is all about not making mistakes. Well, if I work with this equation number 1, I'm less likely to make a mistake than if I work with this equation. This equation I got to multiply by 3, I got to multiply by minus 5, I got to do all kinds of things. So I would always go to the simplest equation to solve for y. Well, y equals minus 14 minus x, right?
Mm-hmm.
So what is that?
So that's y equals negative 21.
No, these two negatives make a positive.
Oh. Plus, so negative 7.
Okay. So both x and y are equal to negative 7. Okay, what else you got?
So it's 3 parts now. It goes 3x minus 2y minus 2z equals 4. And then negative 6x minus 2y plus 4z equals 10. And then 3x minus 4y minus 2z equals negative 13.
All right. Whenever you have 3 equations and 3 unknowns, our plan is to eliminate a variable and create equations 4 and 5. And there will only be 2 variables. So I can eliminate the first variable. I got a bunch of choices here. I could eliminate x, I could eliminate y, or I can eliminate z. What's the first way? What's a good thing to do?
Eliminate x.
Okay, by doing what?
Could you just multiply maybe just the top one by positive 2?
No, you don't need to. In other words, the number 1 already has a 3 there. This has a 3. So why don't I just subtract 3 from 1?
What do you mean?
Well, as I said, you can add or subtract any equations. So if I take equation 3 or 1 and subtract equation 3, it doesn't really matter, I'm going to eliminate x.
So subtract equation 1 from equation 3?
Yeah, to get equation 4. What is equation 4?
So then that, oh, hold on. Let me write it down.
Okay. Now I hate this problem because 2 variables get eliminated. And that's not the typical way these are going to solve. But we'll go through this one. That's all right.
Negative 2y equals negative 9.
So are you subtracting 3 from 1?
Or 1 from, I subtracted 1 from 3.
Okay. So I've got minus 4y minus a minus 2y. What's that equal to?
Negative 2.
Negative 2y, okay. So negative 2y. The z disappears also.
Yeah.
So now I got minus 13 minus 4. What's that?
Oh, that's negative 17.
Okay. So y is equal to 17 halves. In other words, we're able to solve a variable immediately only because 2 variables disappeared at once, which doesn't normally happen, and that's why I don't like this problem. Since I've solved for y, I can go back and substitute it, and now I only have 2 variables. And I can take any 2 of the 3 equations and solve for x and z, because now I have 2 equations and 2 variables. Do you have another 3 by 3? I hate this problem. It doesn't illustrate anything useful for you.
No. That's the only one.
Let me change it then. Let me make this 3z. Okay?
Okay.
Only because this problem isn't going to help you understand this solution. So now what is equation 4?
It'd be
-2y.
negative 2y, and then negative 1.
Okay. Equals negative 17. Okay. Notice that I've gotten rid of x. So I need another equation, 5, where I'm going to get rid of x also. And I want to work with the other two equations. In other words, I got equation 4 by working with 1 and 3. Well, I want to get equation 5 by working with 2 and 3. What can I do to 2, or what can I do to 2 and 3 so that I can get rid of x? Because it's important I get rid of the same variable. What can I do to equation 3 real easily?
Just multiply it by 2.
Okay, so that's 6x minus 8y minus 6z equals minus 26. That's my new equation 3. Now, how do I get equation 5? By manipulating, what do I need to do to get equation 5?
Add them.
Okay, what do you get?
You get negative 10y plus negative 2z equals negative 16.
Now the problem has become one of 2 variables and 2 equations. You know how to solve this, right?
Yeah.
In other words, well, let's go ahead and carry it to fruition here. So let's solve 4 and 5 now.
Okay.
How do I solve 4 and 5?
So then, could you multiply the, like 4 by a positive, or actually you could just multiply it by a negative 2 again?
Yeah. Multiplying 4, yeah, so my negative 2 makes that 34, right? So that's my new equation 4 now. Now, what do I do now?
Add them, so it'd be negative 6y equals what is that? Yeah.
Okay, so y equals minus 3. Now, how do I solve for z? In other words, what's the next variable I can easily solve for?
So just the first equation.
Notice that I can't solve for x at this point. But I can solve for z. Any of these 3 equations that I'm looking at will allow me to solve for z.
So I would just do the first equation.
Yeah, the simple one, right here. So I'll plug in minus 3 for y. So that's 6 minus z equals minus 17. Move the z on the other side, the 17 on this side, and you get z equals 23. Okay, so z equals 23, and now how can I solve for x?
So then plug in both the y and the z.
Right, into whatever. The simplest one looks like this one. It's got a bunch of small numbers, bunch of positive coefficients. So what was y again? Minus 3 and plus 23. So it would be 3x minus 6 minus 46 equals 4, and now just solve that for x, and you have x, y, and z. So that is the very prototypical 3 by 3 set of equations. And that's almost always the way you're going to solve them, is you're going to come up with equations 4 and 5 where one variable is eliminated, the same one, and then you treat it like it's two equations and two variables and solve that, and then work your way back through to get all the variables. Now, what was it that I didn't like about the problem you gave is that two variables disappeared in the very first step. And that meant that instead of getting an equation 4 or 5, we immediately were able to solve for y. Well, once you solve for y, it immediately makes this a 2 by 2. You can pick any of two of those three equations and solve for both variables.
Okay, so that one was like a multiple choice.
Uh-huh.
So would it be no solutions, or no solution, infinitely many solutions?
Well, we didn't carry it to fruition. Give me the three equations again.
3x minus 2y minus 2z equals 4. Negative 6x minus 2y plus 4z equals 10. 3x minus 4y minus 2z equals negative 13.
Okay. So I'm going to do 1 minus 3. Only because it gives me positive numbers. Right?
Mm-hmm.
Okay. Now I've solved for y. I can go back and substitute 17 halves in for y. And what do I have then? Then I have 3 equations and only 2 unknowns.
So then,
so let me do that. Let me rewrite some of these equations. So the new number 1 is going to be 3x. Well, what's that? That's y is 17 halves. So that's minus 17. Minus 2z equals 4. Which is the same as 3x minus 2z equals 21. So there's my new equation 1. And let's use equation 2. And plug in 17 halves for this y, which means my new equation 2 is minus 6x minus 2y is again going to be minus 17 minus 2z equals 10. Or I'll move that 17 over, make it equal to minus 27. Okay?
okay.
So now we have these two equations and we have 2 unknowns. That's all I need. I've already solved for y, so this is going to allow me to solve for x. What's the simplest thing I can do immediately?
Multiply the top one, or equation 1 by 2.
Don't need to. I got a 2z here and a minus 2z there. I'll subtract. Equation 2 minus equation 1. The reason I'm doing it that way is that's going to leave me a positive 6 over there. Well, the z's disappear, and I get minus 6x minus 3x is minus 9x. So I get x equals minus 3 halves. I've solved for x. I've solved for y. I can go up into this equation right now and solve for z. I'm going to plug in minus 3 halves for x. So that gives me a plus 9 minus 2z equals 27 minus 2z equals 18, z equals minus 9. So I got x equal minus 3 halves, y equals 17 halves, and z equals minus 9. So what were your multiple choices?
No solution, 6, -4, 4, -4, 6, 4, or infinitely many solutions. So none of those.
Well, I undoubtedly made an arithmetic error somewhere. And we could find it if we started from scratch and redid it. But I hate to spend our whole session on this problem.
Yeah.
Especially one that I hate because it gives you the immediate solution right off the bat. So it doesn't illustrate how to solve a 3 by 3. And I don't know where I made my error. But I got to believe that there is a solution. We found it. We solved for all 3 variables. But it wasn't one of the solutions that you have as a multiple choice. What were your answers? Because I could multiply everything by 2. And then I get x is minus 3, y is 17, and z is minus 18.
Yeah, no.
That's not one of them either? All right.
Uh-uh.
Well, I don't know where I made my mistake. But that's definitely the method for solving a 3 by 3. Is you eliminate one variable, get it down to a 2 by 2, solve the 2 by 2 by the way you know how to do it, and then work your way backwards and solve for all 3 variables once you got one.
Okay.
All right, what else you got?
The next one is, what is the correct form of the partial fraction decomposition for 2x minus 3 over x cubed minus x squared?
Okay. Partial fractions always means that your denominator has to have a product in it. Right now it's got subtraction going on. But I can make a product by factoring out an x squared, leaving x minus 1. Okay?
Okay.
How well do you understand partial fractions?
Not very.
Let's start with a simple. If I wanted to decompose this partial fraction, I know that it is something over x minus 1 plus something over x plus 2. In other words, you have to kind of think backwards. If I had this situation, in fact, let's do this. If I said how would you do that?
Just, wouldn't you just add the top
No.
in the bottom?
You got to find a common denominator. The common denominator, when you're dealing with variables, is always the product. So that's the common denominator. What goes here?
1.
No, I'm going to divide x plus 1 into my common denominator. I get x plus 2. In other words, when you're adding fractions, you always have to make sure this fraction is the same as this fraction. You can't change them. And here I could cross out that x plus 2 with this x plus 2, and I'd end up with 1 over x plus 1, right? So this is indeed the same as this. Well, what goes here?
X plus 1.
Almost. 2 times x plus 1. See why?
No.
Well, because this had a numerator of 2. So this has to end up being exactly the same as that. And it is. I could cross out the x plus 1s, and I'd end up with 2 over x plus 2. Okay?
Okay.
Now, I can add the numerators. I can distribute and add the numerators. So I end up with an answer that is the common denominator, x plus 1 times x plus 2. And in the numerator, I have x plus 2 plus 2x plus 2. That's 3x plus 4. So I started with two fractions that had different denominators, and I turned it into this down here. Partial fraction decomposition is going the other way. It's starting with down here, and you want to turn it into that. Well, let me show you how to do it with this one, because the one you gave me is an awfully hard one to figure out for your first partial fraction problem. So, I'm starting here. What do I know? I know that there must be some value. In other words, it has to be a problem like this. Right?
Yeah.
Okay. So now I can say, well, a times x plus 2 plus b times x plus 1 has to equal 3x plus 4. In other words, a times this denominator, x plus 2, plus b times this denominator, x plus 1, all of that has to equal this numerator. Let's go through this and then worry about understanding it. Okay? Now, this gets a little tricky at this point. I can solve for a and b because this is true. Because 3x plus 4 has to equal whatever a is times x plus 2 plus b times x plus 1. Well, I got three variables here and only one equation. How do I solve it? Well, I can let x equal minus 2. In other words, because this is true for all x, I can start picking values of x that are going to allow me to solve for a and b. Well, what would one value be worth picking? Would be minus 2, because it'll make this 0. Okay, well, if I plug in x of minus 2, I get minus 2 on this side. If I plug in x of minus 2 over here, I get b times minus 1. Therefore, b is equal to 2. Now, again, let's go back to this step and let's solve for a. Well, how am I going to solve for a? What if I were to let x equal minus 1? It would make my b term go away. If I plug in x of minus 1, I get minus 3 plus 4, so that's 1. And that has to equal, well, when x is minus 1, this is a. So I solve for a and b by partial fraction decomposition. And a is 1 and b is 2, and if you'll remember, that's exactly what we started with. 1 here, 2 here. The only thing is I did everything backwards. And that's the only way to do partial fraction decomposition. Okay? Is by doing it backwards like this. So, let's try it. It gets really, really complicated as you get harder. And the problem you gave me is fairly difficult. What was it, 3x?
2x minus 3 equals x cubed minus x squared.
Now, this is not a first one to do. This is so hard. It's hard to explain, for one thing. This is not a over x squared plus b over x minus 1. And the reason it isn't, because you have to allow for both an x and an x squared. So what it really is a over x plus b over x squared. In other words, I have to allow for both an x and an x squared, plus c over x minus 1. In other words, there are potentially 3. If I put numbers with a, b, and c, and I said add those 3 fractions, you would come up with this as a common denominator.
And that's all she asked for, is like that as the answer.
Ah, okay.
Yeah.
So that is the answer she wants.
Yeah.
Okay.
And we only had one of those questions on the test, so I don't think that she's like doing this a lot.
No, they're not, because those are so hard they take too long. If she put 2 of them on a test, you'd only have time to do 2 of them almost.
Oh, well, actually this next one is 5x squared plus 12x plus 3 over x parentheses x plus 1 squared.
Like that?
Yeah.
All right. What are our 3 denominators going to be?
So, would it just be x, and then x plus 1, and then another x plus 1?
Another x plus 1 squared. Notice that if I had these 3 denominators, the lowest common denominator would be this over here. It would not be that times that times that. And that's why you have to do it this way. And this is an A, a B, and let's see, it's been a while since I've done partial fractions. I only get a student about once a year that has to do partial fractions. I'm amazed that you're getting it in Algebra 2 to this level. I'm trying to remember if this is a C or if this is a CX plus D.
Well, that one, this problem asks for like numbers on top. So I think it...
So this one, it wants you to solve the whole thing.
Yeah.
Okay. Well, I'm going to just try a C and see what happens here. So what can I say about 5x squared plus 12x plus 3 has to equal, remember that if I add all three of these together, I'm going to get a numerator. Add these three fractions together, and what are you going to get? In other words, just this part here. Knowing that this is your common denominator. So what is the A part?
X.
Remember that it has to end up being the same thing as this. So I need an x plus 1 squared, and I need the A. Same thing, right?
Yeah.
Okay, what's the B part look like?
X plus 1.
Well, we have to multiply it by x, and we have to multiply it by an x plus 1. Remember, the whole goal is to not change that fraction. And if you reduce this, you will see it's b over x plus 1. Okay? The same philosophy goes for c. It's going to be cx over x times x plus 1 squared. Haven't changed it. This fraction is the same as this fraction. This fraction is the same as this fraction, and so forth. You with me?
Yeah.
Okay. So now that I've got it like this, I can equate the numerators. You see why? In other words, if I complete this process, I'm going to add the numerators all together. I'm going to have this denominator, and it's going to equal this, which means that this numerator equals this numerator, because their denominators are the same. So the next step would be to set 5x squared, this numerator on the left, equal to this numerator on the right. Well, I got to do some algebra here. This is ax squared plus a 2x plus a, excuse me. Right? That's just doing that. Let's do the rest of it. Plus bx squared plus bx plus cx. With me?
Yeah.
Okay. So now I've got 5x squared plus 12x plus 3 equals all of this. Well, let's combine some of this over here. I got a couple of x squareds. I can factor out the x squared and have a plus b times x squared. That's combining that and that. How much x's do I have? I have a 2ax there, a bx there, and a cx there. So it would be plus 2a plus b plus c all times x, like that, plus one number, a. That on the right-hand side is equal to this numerator on the left-hand side. What can I say about a plus b? In fact, what can I say about a? If this is equal to all of that, then this a has to equal this constant. A plus b has to equal 5, and 2a plus b plus c has to equal 12. You see why? All I'm doing is equating coefficients. So I know that A equals 3 right off the bat. Well, if A plus B has to equal 5, then B equals 2. So now I've got 6 plus 2 plus C has to equal 12. C must be 4. And there's your answer. A is 3, B is 2, C is 4. So A is, excuse me, what did I say again? 3, 2, 4. So this is 3, 2, 4. And if you weren't sure whether that's the right answer or not, then what we would want to do is add these three fractions and see if I don't get what I'm supposed to get. In other words, we work backwards to get this answer. So if you want to check this answer, then start here and work forward. And you will get this. Okay? And there is a more complicated method, yet still that if you have, I can't remember, I'd have to look it up, but I don't think you're going to get problems like that. In fact, I'm amazed you got something this hard.
Yeah, it's pretty terrible.
This is a pretty hard problem. Yeah. And, you know, partial fractions is not something that they teach everybody anymore. What school do you go to, Jade?
Columbine.
And it's Algebra 2, not Honors Algebra 2?
No, I'm in pre-calc.
Oh, you're in pre-calc. Okay. Well, I apologize. Even most of my pre-calc students never have to do partial fraction decomposition. The only place you really need partial fractions is when you get to calculus. When you go to do integrals, partial fractions are extremely useful because you don't know how to integrate that, but you do know how to integrate the sum of a bunch of stuff. So it's easy to integrate sums and differences. It's very hard to integrate products. There is no tool for integrating this thing on the left here. But if I can turn the thing on the left into the thing on the right, then I can integrate each term. So that's the reason we need partial fractions, and that's also the reason they don't tend to teach it in pre-calc, is because you don't really need it until you get to calc. There is no application in pre-calc that needs you to decompose partial fractions. It's only when you get to integral calculus that it's needed.
I don't plan on taking that, so.
Well, at least not this year. You might next year. You a senior or junior?
Senior.
Okay. Well, you might in college. And then you would need this technique.
Alright, this one is what third degree polynomial function has x minus 1, or I mean x equals 1 and x equals 2 plus I as two of its roots.
Okay. If x equals 2 plus I as a root, what's another root that they didn't tell us about?
Negative, or x equals negative 2
No,
plus I.
it's the conjugate, which is always just change the sign in the middle.
Oh.
Okay. So we know those are the three solutions. So what are the three linear factors?
So x minus 1 and then
In other words, you don't do it any different. You do it just like it was a real number. Okay? You with me?
yes.
Now let's let's remove the inside parentheses. Well, this becomes x minus 2 minus I. This one becomes x minus 2 plus I. And we still have our x minus 1. So now we want to get the multiplying. In other words, to come up with the polynomial they want, so all we have to do is multiply these three things together. What two should I multiply together first?
The x minus 2i.
And the reason is that because these imaginary solutions come in pairs, it turns out that that linear factor times that linear factor will get rid of your I. Let's do it.
Okay. So, x squared minus 2x plus ix, and then negative 2x minus ix.
Hold on. Let's follow a pattern that we can stick with. Your pattern was that times that, that times that, that times that. The next thing you're going to do is that times that, that times that, that times that. Don't jump all over or you'll forget one.
Okay, so then it's plus 4 minus 2i, and then it's minus ix, and then plus 2i, and then minus I squared.
Okay. Everything with an I in it's going to cancel except the I squared. Notice that this ix cancels with that one. This 2i cancels with that one. And we're left with x squared. We got a total of 4x minus 4x. What's minus I squared equal to?
1.
I squared is equal to 1. So minus I squared is plus 1. Plus this 4 gives us plus 5. That's the result of that times that. Notice no more I. Now we have to multiply that by x minus 1 and we'll have our answer.
Okay, so...
Well, their question was they just wanted a polynomial, a third degree polynomial? What exactly did they want? Because this can be worded in a bunch of different ways.
Yeah, it just says what third degree polynomial function.
Well, this will give it to you. You clearly know how to multiply a trinomial. Well, let's go ahead and get an answer. What's this times this?
X cubed minus 4x squared plus 5x. Then negative x squared plus 4x minus 5.
Okay. How many x squareds do we have?
Negative 5.
How many x's do we have?
9.
How many numbers do we have? There's your answer. And it's easier when you have a problem like this. There's a reason why you should multiply this by this first, because it actually reduces better. If you multiply this by this, you'll have all kinds of i's. And then you're going to have to multiply that by that. It's going to be tougher. I think it's easier to get rid of the i's as soon as possible. And you always get rid of them by multiplying the two linear factors that have the I in it. That I, you can be guaranteed that you will not have an I after you multiply these two together. And that's true of no matter what the problem is. In other words, if they give you 3 other solutions, the two imaginary solutions, when you multiply those two together, you get rid of the imaginary number. Okay? As long as you know I squared is equal to -1. That's a key thing when you're dealing with any kind of processes on imaginary numbers.
Okay.
Any
yeah, that was my
that was your last one? Okay.
Yeah.
Any other questions? I can't believe the difficulty of the partial fractions one they gave you.
Yeah.
Only because when you have a square in the denominator, you have to allow, in other words, if I've got 1 over x squared times x minus 1, I have to allow for an x, I have to allow for an x squared, and I have to allow for the x minus 1. So this problem would decompose like that, and then you would proceed to do the rest of it also. Typically, the problem would be that. And then I only have to allow for an x and an x plus 1, x minus 1. In other words, if you have a linear factor times a linear factor, then it's relatively easy. It only gets really difficult when you start complicating up the denominator and you add squares or cubes or things like that. Then it makes it much harder. But a typical decomposition would be that. I got to believe that on a test you're going to get something that looks like this, not something that has an A, B, and a C.
Yeah.
All right. Well, if you don't have any other questions, I will let you go.
All right. Have a good night.
You too, Jade. Talk to you next week.
All right. Bye.